the first assignment. This assignment will be due next Tuesday by 5 p.m. and on next Friday, not the coming Friday but the one after, we're going to have our first quiz. So today what we're going to look at, we're going to probe further the Gauss's law and some of its applications. I would like to start off by finding out the field due to an infinite sheet of charge. All right. Attention please. Suppose I have a sheet of charge positively charged. So there are positive charges all the way around on this sheet. The sheet has negligible thickness. And these wiggly signs denote that it's an infinite sized sheet. So this wiggly sign shows that this sheet actually is expanded sideways so that it's of infinite expanse. And these wiggly signs show that this sheet is actually vertically extending to infinity. So it's a huge sheet. Of course this is an approximation. Now what I would like to find out is that if this charge is uniformly distributed over the surface, and I can define a sigma, which is a surface charge density, which is the amount of charge in a small area of this sheet, and this is uniform. So if you're here, take a small area, the amount of charge in that area would be the same as the amount of charge in any other area, in any other equal area on the sheet. So the charge density is uniform. And here we're talking about charge per unit area. We can talk about charge per unit volume, charge per unit length, and so on. So what we are interested in is finding the electric field at some point, say P, which is at a distance, some distance away from this sheet. Alright? So if I look at this sheet, the first question is, I would like to use Gauss's law. That's the first point. I don't want to use Coulomb's law, because if I were to use Coulomb's law, I would have to take small area patches, find the electric field due to each patch, and then integrate along the x direction from minus infinity to plus infinity and along the y direction from minus infinity to plus infinity. I would like to avoid this. Rather, I would like to use the Gauss's law. So how do I go about in solving this problem? Whenever you have a problem that you'd like to tackle by Gauss's law, it's always nice to think about the symmetry of the problem and find out, if there were a field at P which I am asked to find, what is the direction of that field? Is there a unique direction that I can choose which conforms to the symmetry and the geometry of the problem? So could you please tell me, if you're at point P, what is the direction of the field? It's outward. It's away from the sheet, because this is a positively charged sheet. It's away from the sheet and it's going to be normal to the plane of the sheet. So it's going to point in this direction. This is the electric field at point P. Now I don't know its magnitude, but I know its direction. So if I take any other point that is at the same distance away from this sheet, so that this line is at a distance, say y0 from the sheet. Since this is an infinite expanse of charge, any other point that I take on this line will have the same magnitude. So I draw equal length arrows. And all of these arrows will be pointing away from the sheet. Okay? So this is something I know from symmetry. There is no other unique direction that I can choose because this sheet is infinite. Alright, if I am closer to the sheet, I move closer to the sheet and I choose a point Q, I still know that the electric field is pointing outwards, not radially outward because there is no concept of radius here, it's just pointing normal to the sheet. So I am standing here, I am the sheet, the electric field is pointing straight away from me and it's making an angle of 90 degrees with my surface. And intuitively one would assume that this electric field could have a different magnitude than the electric field at point P because you're closer to the sheet. So this is something we would like to find out. Alright? But this sheet has two sides to it. There is a right side and there is a left side. So if I choose another point R on the other side of the sheet, there must be an electric field there as well. There's nothing special with the right or the left direction. Both of them are on equal footing. There is no preference as far as space is concerned. So there has to be an electric field at point R as well. What's the direction of the field at point R? It's going to be towards your left. Again, normal to the surface. So I can draw an area vector here. Now if I draw a line, and this line, in other words, if this point R is at the same distance as point P, what would you expect for the magnitude of the electric field? It would be the same because there's no difference between the right and the left. Alright. Now, based upon this observation, I would like to choose a Gaussian surface. Okay? Now, could you please raise your hands and tell me if you could think of such a surface that conforms to this symmetry arrangement? Conform का मतलब मुताबिक है कि ये जो हमने बात की है डायरेक्शन ऑफ फील्ड के मुतालिक, मैग्नीट्यूड ऑफ फील्ड के मुतालिक, उससे मुताबिकत रखता हुआ कोई हम सरफेस बना सकते हैं कि नहीं? आप बताएं.
We can take a cylinder passing through the sheet and both of the points R and P
are on its end caps. And what about the orientation of the cylinder? Should it be slanted or normal to the surface?
normal to the both points.
Right. So let me draw this sheet again. I'm drawing a different perspective view so that I can easily draw the cylinder. So this is a positively charged sheet. It doesn't have any thickness. Since it doesn't have any thickness, it doesn't matter whether it's an insulator or a conductor, but we'll come to that point. I want to find the field at point P. This is given. So what I choose to draw a cylinder. Cylinder of course has a curved surface and two end caps, because any surface that I choose as a Gaussian surface has to be closed. Closed means someone who's outside the surface cannot go inside the surface without penetrating the surface. There is no hole in the surface by which an external object can enter the surface. So it's a closed surface. So I draw a cylinder. It's a Gaussian surface and of course it's just a figment of my imagination. There's no real cylinder there. This cylinder has a curved surface. This curved surface makes an angle of 90 degrees with the sheet. So it's normal to the sheet. If this is normal, this end cap is parallel to the sheet. And I would like to extend this cylinder to the other side as well, such that the other point R is in the middle of the other end cap, and the amount of length that extends out of the cylinder to the right is the same as the amount of length that extends to the left. So it's a very uniformly placed Gaussian surface. Okay, and I already know that the field here will have the same magnitude as the field here. Okay, now there are three surfaces on this Gaussian surface. There is a curved surface and there are two end caps. So the flux through, let's call this Gaussian surface S. The flux through S will be given by the flux through the curved surface plus the flux through end cap 1 plus the flux through end cap 2. I call this 1 and I call this end cap 2. Now what's the flux through the closed surface?
0.
Why is the flux through the closed surface 0? आप बताएं, blue shirt में. What is perpendicular to the field? Right. So this curved surface is parallel to the field. So if I draw any area vector, if I take a small patch and I draw the area vector, some dA, this area vector is normal to the electric field. So the electric field is skimming the surface, it's just running parallel to the surface, it's never piercing this curved surface. So the cross product between all such fluxes will be 0. Sorry, the dot product. So this is 0. Now I have to find the flux through this end cap. The electric field at point P is given by EP. Okay, and if I take a small area on this surface, dA, its area, the area vector dA is also pointing in the same direction as the electric field. So this phi1 is really equal to EP cross product, dot product with dA summed over end cap 1. Okay? Now the electric field and the area vector are locally parallel. So the angle between them is 0. So cosine of 0 is 1. So I can just take the magnitude of EP and dA like this. Everything is inside the integral. I'm integrating over end cap 1. Now is the electric field uniform on this end cap? Yes, it is, because all such points are at the same distance. So I can take electric field outside the integral and I can take the area of the integral or of the area, the integral of the area. Okay, let's call this area A, capital A. So this turns out to be EP capital A. The integral of the area is just the area of the end cap. Okay, so what is the flux through surface 2? The flux through the surface 2 is going to be the same, because here the electric field, even though it's pointing in the opposite direction, the area is also pointing in the opposite direction. So the flux through this end cap is still EPA. Therefore, the flux through S is equal to EP or A. EP and ER will have the same magnitude, right? So we can just call it EP. EPA plus EPA to EPA. So this is the total flux through this curved surface. Now what, by virtue of the Gauss's law, what should this equal to? It should equal the charge enclosed by this Gaussian surface divided by epsilon naught. So I have 1 over epsilon naught, and what's the charge enclosed by this surface? बताएं, red shirt में please. R तो यहाँ पे कोई नहीं, कुछ और बात करो. Sigma A. This A goes away and I'm left with EP equals sigma over 2 epsilon naught. Now does this electric field depend upon how far are you from the sheet? No, it doesn't. This is something quite surprising at the outset. At first you look at this result, it seems very surprising because you're moving further and further away from the sheet. The electric field still remains constant. It's sigma over 2 epsilon naught. This is only because this sheet is of infinite size. If the sheet were not of infinite size, the result will not hold true. Since this sheet is of infinite size, the further you move away from the charge sheet, the amount of charge that you always see doesn't change. That's why the electric field is independent of how far are you from the sheet. So if you could construct a charged sheet through the universe of extremely large dimensions, its electric field will be uniform throughout space. No matter how far you go from that infinite expanse of charge, you'll see the same electric field. Alright? However, on the right of this sheet, if I would like to write a vector EP, this vector would have a magnitude equal to sigma over 2 epsilon naught and a certain direction. Suppose I call this the x direction. So I will put an iota here, unit vector iota. So the electric field at P will have a certain direction, and the electric field at at R will have the same magnitude as the electric field at P, but it will be in the opposite direction. Okay? So if I were to plot, this is the distance x from the infinite sheet of charge, and my sheet of charge lies here. And if I were to plot EP, just the magnitude, or if I were to plot EP respecting the sign of EP, okay, then the kind of plot I would make is that for negative values of x, that is when you're to the left of this charge, the electric field is minus sigma over 2 epsilon naught. Alright? This is sigma over 2 epsilon naught. But since the electric field is pointing in the other direction, I've given it a negative, I put it below in the fourth quadrant. And to the right of this sheet, the electric field is positive, which means it's in the plus x direction, and it has a constant magnitude. And this height is sigma over 2 epsilon naught. Do you get this point? Alright. So is the electric field uniform to the right of the sheet? Yes, it is. Is it uniform to the left of the sheet? Yes, it is. But what about x equals 0, where the sheet of charge exists? Is the electric field continuous? No. There is a discontinuity in the electric field. And how much is this discontinuity? The discontinuity in the electric field is this value of the electric field minus this value of the electric field, and that is sigma over epsilon naught. This discontinuity is sigma over epsilon naught. So the discontinuity turns out to be equal to 1 over epsilon naught times the surface charge density. And this is a general rule. Electric fields can be discontinuous if there is charge on a surface. If charge only resides on a surface, the electric field to one side of the sheet will be different from the electric field to the other side. Now this is a very important result. In our previous example, in which we had a uniformly charged sphere, we drew the electric field versus the distance from the center of the charge. And we noticed that the electric field varies linearly up to the radius of the sphere, and then it drops as 1 over r squared. So here is the electric field continuous? Yes, it's still continuous. The derivative is not continuous, but the field is continuous. So at capital R, the electric field has just one value. Whether you approach capital R from the left or from the right, you get the same value. So the electric field is continuous, even though its derivative may be discontinuous. Which means that charge does not only lie on the surface of that sphere. And we already know that sphere we were talking about was uniformly charged. However, whenever you have a situation like this, in which charge only exists on a surface which doesn't have any thickness, the electric field becomes discontinuous. And we'll use this result later. Alright, any questions up to this point? आप पूछें? Here, the electric field, we cannot define the what is the electric field at a point charge? You cannot define it. Which is another way of asking, what force does a charge exert on itself? Right? Electric field is force per unit charge. So if I were to ask the question, what is the electric field at the point of a point charge? It's like asking the question, what force does the charge exert on itself? But that's not a valid question. Alright? Ji. No. Because in this example, we have to take the charge enclosed by this surface. Now this is a surface. Every surface is the boundary of a volume. Correct? If I draw any surface, the surface doesn't have any thickness. But inside the surface there is a volume. Okay? So this is an important statement I can write. Every surface is the boundary of a volume. And Gauss's law asks you to know the charge inside that volume. And this is another way of saying what's the charge enclosed by the surface. So you take this volume and see how much charge is enclosed by this surface, or how much charge exists inside the volume, on whose boundary this Gaussian surface has been drawn. And the only charge that exists is on this sheet, and it will have an area that is just a copy of the area of the end cap. So this is the area of charge that is enclosed by the Gaussian surface, and this area is also capital A. It's going to be the same as the area of this end cap, and it's going to be the same as the area of this end cap. ठीक समझ आ गई? चलें आगे चलते हैं. सॉरी मैं आप अगले दफा आपसे पूछूंगा. All right. Now suppose instead of one plate of charge, I have two plates, like a capacitor. And one plate, both of these plates are of zero thickness, right? They are of infinite size. And this plate is positively charged with a uniform charge density sigma, and this plate is negatively charged also with a uniform charge density of sigma or minus sigma, no matter how you would like to look at it. First of all, so the point is we would like to find the electric field at some point P in between the plates. Now there is a distinction between the right and the left of this plate. The right of this plate is different space from the left of this plate. Do you agree with that? The isotropy of space has been broken. Isotropy का मतलब कि तमाम स्पेस अब एक जैसी नहीं लगती. यहाँ पे तमाम space to the right and to the left were on equal footing. You cannot differentiate right from left. This is the law of physics. Physics does not depend upon whether you perform an experiment to the right of this sheet or to the left of this sheet. Physics will remain the same. However, this situation changes here. The left of this sheet is not the same as the right of this sheet, because to the right there is a negatively charged plate. Alright? So, the first question is, after this isotropy has been broken, we would like to find out what the field is in between the plates. For that we have to choose a Gaussian surface, and for that we have to have some intuition of what the electric field's direction should be. Now remember, these are infinitely charged sheets. So first of all, could you tell me the direction of this electric field? It's going to start at the positive charges and end at the negative charges. So the field is going to point from positive to negative. Like this. This is the electric field at point P. And is it normal to the surfaces? Yes. Right. Is it normal to both surfaces? Yes. And what's the electric field to the left of this sheet? Is there any electric field to the left of this sheet? Remember, these are infinitely sized sheets. Suppose I take a dipole, positive, negative. I would like to find the electric field distribution due to this dipole. Of course, the electric field will be non-zero here. It will start at the positive charge and end at the negative charges. And there will be a field here as well. But in general, there will be a tendency for the electric field lines to curve. But still there will be some field to the right of this charge and to the left of this charge. Correct? This is the field due to a dipole. Now instead of taking one negative charge, what I do is that I take this one positive charge and take an infinite series of negative charges. And then I repeat the process on this side. We take an infinite series of positive charges. The net effect of this is that all these electric field lines will be forced, or they will have to point towards this negative series of charges, because the curvature of these lines will be so high that no lines can actually escape to the other side. Because now this positive charge is seeing an infinite series of negative charges. The pull from these negative charges will be extremely high. This curvature, in other words, will be so high that no field lines will dare go on to this side. So the net result would be is that there will be electric field pointing from the positive to the negative charges in between the plates. However, there will be no electric field to the left of. Suppose this charge is captured or kidnapped from this positively charged sheet. It's just one charge. I would like to draw the electric field due to this configuration. The electric field due to this configuration will look like this. Positive, the fields will go from positive to the negative sheet. Right? This is what this field pattern will look like. Now if I put another positive charge here, the curvature of these lines will go away, because between two positive charges the electric field goes to zero, because both of them are repelling one another. So at the end what you will observe is that the electric field lines will point from the positive charge sheet to the negative charge sheet, and they will always be normal to the plane of these sheets. And there's a reason for that, and this is something I'll explain. The summary is that in such a parallel plate capacitor, which comprises infinitely sized sheets, the electric field is pointing from the positive to the negative sheet, and there is no electric field to the left. Now it's quite easy to determine what the electric field at point P is. First of all, from the previous result, could you tell me whether this field would depend upon where P is in between these plates? Would it be different close to the positive charge? Would it be? No. It should actually be the same wherever you are in between these parallel plates. So between infinitely sized parallel plates, the electric field is truly uniform. So this is one procedure of how do we prepare uniform electric fields. Now we would like to find out the magnitude of this field. Could you, I give you 2-3 minutes to draw a Gaussian surface and find the magnitude of this field, please. पहले काम करो. Yes. कौन सी गॉसियन सरफेस बनाई? बॉक्स. आपने फील्ड P पे फाइंड करनी है, ठीक है? अल्हम्दुलिल्लाह. No. Good question. One question I would like you to ask before we move ahead. In this question, instead of making a Gaussian cylinder, could we make a Gaussian cube? Could we make a Gaussian cube? Who says no? Why no?
Sir, because uniformity नहीं रहेगी कि अगर हम उसको change करेंगे तो अगर हम cos को change करेंगे तो effect जो आपका होगा वो
नहीं, a cube that is whose sides are normal to this sheet. If you orient this Gaussian cylinder, you slant it, the results will still change. But if I have a cube that just pierces this surface and it has two plane surfaces, the end ones that are parallel to this plane, would it work? होने दो लेकिन इलेक्ट्रिक फील्ड लाइंस उस एरिया के हमेशा नॉर्मल होंगी, so the flux to that surface will always be zero. So yes, in this particular example you can also choose a cube or a cuboid. Very good question a student asked, and I think this is worth mentioning. Right? You can choose this cube. The end faces of this cube, this or cuboid, this area is normal to the surface, so it's parallel to the electric field, and so is this. All other surfaces are parallel to the electric field, so the areas are normal to the electric field, so the flux through 1, 2, 3, 4 surfaces is 0, and the flux through these two surfaces is non-zero. In fact, you don't even have to choose a cube. You can choose an arbitrary cross section of an object which runs normal to this surface, right? It doesn't have to be a cube or a cylinder. You just have to make sure that the flux through the other sides of this structure is 0. So you don't have to choose a Gaussian cylinder in this particular case. Okay, now please find out the field at point P due to Gauss's law. Draw the Gaussian surface. What kind of Gaussian surface would you draw? Please draw the surface first. Draw a Gaussian surface. कोशिश करो, कोशिश करो. So you want to simplify your problem, you want the flux of the curved surfaces to be 0. Right?
You can take either side, the curved one or the faces, depending on the...
No, you can't take a vertically standing cylinder because then the curved surface will have areas pointing in different directions. Now another question that has emerged. I think it's good you coming up with these counter examples. In this infinitely sized sheet, please pay close attention. बातें नहीं मैं बर्दाश्त कर सकता. What if I were to take a Gaussian cylinder that is vertical? So it's a Gaussian cylinder that is vertical and it pierces the Gaussian this sheet of charge. So if I look at this sheet of charge from the top, if I look from here, I see the sheet from the top, I see the top of the sheet, even though I cannot really look at the sheet because it's infinitely sized. But let's assume I'm far away, I'm some supernatural being and I'm really far away, I can go beyond infinity. I see the top of the sheet and I see this cylinder. One half of this cylinder is here and one half of this cylinder is here. And this is the cross section of the cylinder that I've drawn. Now is this a good surface to draw as a Gaussian surface? Why not? आपने सवाल पूछा, आप ही जवाब दें. Why not? Right, because even though the electric field is always pointing like this, here the area vector is pointing in some direction, here the area vector is pointing in this direction, here the area vector is pointing in another direction, or in other words the area vector is pointing radially outwards, whereas the electric field is in a planar direction. So the angles between the electric field and the area vector are constantly changing. So it will be very cumbersome to find the flux through each surface and then integrate. So this is not a good surface to choose. Coming back to my question, has anyone been able to draw a Gaussian surface that actually helps me find this electric field? Anyone? Ball points ko na karen please. Shabash, really good. So you have a one end cap on this charge, one here.
फिर ये confusion है. सर इसमें सर्किट बन चुका है. इसमें सर्किट बन चुका है.
सर्किट नहीं, सरफेस बनानी है. Good. No, not so good. But you cannot find the electric field here. You want to find the field here, you cannot find it with this surface. तो इसका दूसरा end cap कहाँ है?
Open end भी हो सकता है.
No, it has to be a closed surface. Every Gaussian surface is closed. Good. Just one student? किधर बनाए? Good. Two students दिखाए. यानी एंड कैप्स दोनों बाहर हैं, तो P पे फील्ड कैसे फाइंड करोगे?
सर सरफेस पे उसके एंड कैप्स नहीं आएंगे.
But you would need to know that the field here is the same as the field here. You don't know that at the outset.
Sir, is the answer if we
This is good. Good.
is the answer correct? Sir, one more thing.
Sigma, what is this? No, not 2. Let me draw this surface for you. I want to find the electric field at point P. I draw a Gaussian cylinder whose end cap has P on it, and it has curved surfaces that are normal to the sheet. And then the sheet goes, and then this Gaussian surface goes to the other side, and then there is another end cap here. In this region, the electric field everywhere is 0. So the flux through this region to the left of this sheet is 0. What's the flux through the curved surfaces? 0. So you're only left with the electric field at point P. And you already know that the field is the same at different points on this end cap. So I can take EP into the integral of the area of this surface, which I just call A, and this must equal the charge enclosed by this surface. And what's the charge enclosed? I look at this cross section of the sheet and find how much charge is inside this sheet, because this is the charge that is surrounded by the surface, and this charge is sigma times A, and I have to divide by epsilon naught. By virtue of Gauss's law, the electric field at point P equals sigma over epsilon naught. So it's twice of the electric field here. In other words, when we learn about energy, I received an email from a student about energy. When we learn about energy, all of the electric field's energy that was on this side of this sheet has come to the other side. It's now in between the plates of the capacitor. So this is the electric field between two parallel plates of a capacitor. Of course, it has a certain direction as well, so you can put a vector sign here, but then you have to put in a unit vector here. Now, could you draw the electric field versus X? The magnitude of the electric field versus X. Suppose this is the position of the positive plate and this is the position of the negative plate. What will a plot of the electric field look like? Straight line everywhere? और दोनों तरफ क्या होगा? 0. So electric field is 0 here. It's 0 here. And it's sigma over epsilon naught here. So there is a discontinuity here. There is a discontinuity. How much is the discontinuity? Sigma over epsilon naught, and that's just 1 over epsilon naught times the surface charge density on this plate. What's the discontinuity here? It's minus sigma over epsilon naught. Be consistent. Here you're going from left to right. There's a jump in the electric field. So the discontinuity is plus sigma over epsilon naught, and that tells you it's a positively charged surface of charge. Just a surface of charge. And whenever there is just a surface of charge, the electric field sees a discontinuity. Okay? Now here, what's the discontinuity? Minus sigma over epsilon naught. Because you're going from positive to negative, it's a downwards jump. And that tells us that the surface charge density is minus sigma. आप आगे पढ़ा लो प्लीज।
सर वो कह रहे कि अगर एरिया बड़ा करेंगे तो सिग्मा चेंज हो जाएगा। मैं कहता सिग्मा कैसे चेंज हो जाएगा?
Now we would like to talk about fields inside conductors. सपोज आई हैव अ वॉल्यूम. देखो जब मैं लफ्ज इस्तेमाल करता हूं ना वॉल्यूम, इसका मतलब आपको पता होना चाहिए. वॉल्यूम का मतलब है कि कुछ सरफेस है उसके अंदर मैटर है. वॉल्यूम इज 3 डायमेंशनल. सरफेस एक शीट है जिसको आप रोल कर सकते हैं, बट इट डजंट हैव एन इंटीरियर. इट्स द सरफेस इज द बाउंड्री ऑफ अ वॉल्यूम. Okay, so if I take this table as my volume, if I only paste paper on its surface, on its top surface, I'll get a surface. I can get a closed surface or an open surface. But then there's volume. Now suppose I have a volume of matter. Now this volume has an inside as well. There's mass inside this volume. So it's 3 dimensional. And suppose it's a metal. Now metals have free charge carriers, which means there's a sea of electrons. You apply a force, an electric force to these electrons, they can move. Okay? So if I have a charge Q, what force does it experience? आप बताओ, चार्ज Q है, इस पे कितनी फोर्स लगेगी? इलेक्ट्रिक फोर्स. No, there's a charge and you would like to find out does it experience some force. What would you need to know? If I place a charge here, how can I tell that it's experiencing a force? Right, there has to be an electric field at the point of this charge. So if I multiply this charge with the electric field at this point, I will get the force on the charge. But whenever there is a force on a charge or the charge is of course a mass as well. It could be an electron. It has a mass, so it can accelerate. So this force will equal some mass times acceleration. Mass times dV by dt. Now if there is some electric field, there is some force, there is some acceleration, so there is some non-zero dV by dt. And if the velocity is 0, you cannot have an acceleration. So there is some finite velocity and it's changing with time. This means that the charges are moving inside the conductor. Okay? Now when charges are moving, there is acceleration, you cannot have equilibrium. Equilibrium really means that there is no acceleration of the charges. Everything is moving either with uniform velocity or it's not moving at all. So if you have a metal in a state of electrostatic equilibrium, then what does it imply? It means there's no acceleration of the charges, which are free to move anyway. How can there be no acceleration? There is no force on the charges. How can there be no force on the charges? There is no electric field. There are charges. The charges have some units. I mean, they could be 100 coulombs of charge, 1 coulomb of charge, 1 nanocoulombs of charge. There are free electrons. There is no denying the fact that there are free electrons which carry charge inside the metal, but they're not accelerating. So if a metal is in a state of electrostatic equilibrium, the charges cannot accelerate. It means that inside the volume of a metal, the electric field is always 0 inside the conductor. Alright, now if the electric field inside the conductor is 0, I want to use Gauss's law in reverse. I want to tell what is the charge inside a conductor. So if I draw a surface that is inside the conductor, I know that the electric field through this Gaussian surface is 0. Okay? So here the field is 0, here the field is 0, everywhere on this dotted periphery, which is a surface, the electric field is 0. by virtue of Gauss's law. So if the field is 0, the flux through this surface is 0. What does this tell me about the charge inside this volume? 0. That's the Gauss's law. So if the electric field inside this surface, or electric field on this surface is 0, which means the flux through the surface is 0, the charge inside this region, the charge enclosed, must also be 0. It can never be non-zero. So inside a conductor, the charge is always 0. However, we know that we can charge a conductor. So if this is a parallel plate capacitor, there is a metal and we can put charge on it. That's what happens in capacitors. You all know capacitors. You can put positive or negative charge on a metal, on a conductor. So there can be charges in a metal volume. But Gauss's law is dictating us that there can be no charge in the interior of a conductor. So this is like paradoxical. ठीक है? एक तरफ आप कह रहे हैं कि चार्जेस तो एग्जिस्ट कर सकते हैं कंडक्टर पे, वी कैन चार्ज अ कंडक्टर एज इट हैपेंस इन कैपेसिटर्स. दूसरी तरफ गॉसेस लॉ कह रहा है कि चार्ज एग्जिस्ट नहीं कर सकता बिकॉज द इलेक्ट्रिक फील्ड इनसाइड अ कंडक्टर इन अ स्टेट ऑफ स्टैटिक इक्विलिब्रियम इज 0. ठीक है, ये वही बात होगी, इमाम मुझे रोके है तो खींचे है मुझे कुफ्र. एक तरफ से आप उस तरफ खींचे चले जा रहे हैं, दूसरी तरफ से एक दूसरी तरफ खींचे चले जा रहे हैं. इट्स लाइक पैराडॉक्सिकल. Now how do we resolve this situation? Suppose I make another Gaussian surface. This time I make this Gaussian surface closer to the surface of this metal volume. Still the charge inside this green Gaussian surface will be 0 because the electric field inside the conductor is 0. So the only possibility of storing charge on a conductor therefore is that the charge is stored on the outer surface of a conductor. It just resides on the outer surface. Okay, so if I were to put charge on this conductor, all of that charge will go on the outer surface. So all the charge in a conductor is actually not in a conductor, it's upon the conductor. It's on the outer surface of a conductor. And you can write this down. और इसके मैं आपको बहुत सी खूबसूरत एप्लीकेशंस बताता हूँ भी. जी इलेक्ट्रिक फील्ड अप्लाई करें या ना करें, whenever a metal, हाँ उसकी भी मैं आपको एग्जांपल्स दूंगा. ठीक है जी, ऊंची बोलो, सबको आवाज है.
This means that the charges are only on the surfaces. For example, if you put a negative charge on the surface, so those electrons cannot move inside the conductor, or they're static in the position.
Alright, suppose this is a positively charged conductor. Let me answer this question. There's no charge inside the conductor. But what does that mean? Aren't there any other electrons inside the conductor? Are there any other electrons inside the conductor? Yes, they are. But why then is there no charge? Because the net charge is 0. As many electrons, so many protons. The net charge inside this conductor will be 0. So if you take a piece of metal, don't charge it. The number of protons is the same as the number of electrons, even though the electrons are free. But once you put external charge on this conductor, all of that charge is an imbalanced charge and it resides on the surface. And if the surface charge density is sigma on the surface of a conductor, we can always find out what the electric field is outside the conductor. Let me do that for you. Suppose I have a volume and the surface is charged, say positively charged. It's positive charges everywhere. And the charge density, suppose, is at a particular point it's sigma. Okay? At some point P, suppose the charge density is sigma. Now I'm not claiming that this charge density is uniform on the surface. देखो मेरी बातें ये जो मैं छोटी छोटी बात भी करता हूँ ना, उसमें कोई ना कोई सटलिटी है यहाँ पर, कोई ना कोई उसके अंदर कोई पैगाम है. अब यहाँ पर मैं ये कहना चाह रहा हूँ कि ये एक आर्बिट्ररीली शेप्ड सरफेस है. अब मैं यूनिफॉर्म चार्ज डेंसिटी की बात नहीं कर रहा, मैं एक पॉइंट लेता हूँ P. इस रीजन में जो सरफेस चार्ज डेंसिटी है वो सिग्मा है. So if I have charge Q that is distributed on this surface, this charge in general will not be uniformly distributed. Why is that the case? Could anyone tell me? Yes. Exactly, very good. Charges generally tend to accumulate on sharp edges, like points. That's why you have point conductors. Lightning conductors are pointed. So charge would like to accumulate in this elbow region, in this case. So you have a surface like this. There would be a tendency that charges accumulate in this region. So the charge density will be higher in this region. So in general, if you have an arbitrarily shaped conductor, the charge density on the surface may not be uniform. However, for a spherical conductor, the charge density tends to be uniform. So suppose at this point P, I would like the surface charge density to be sigma, and I would like to find out the electric field at some point Q, just outside the conductor. And I don't want to go very far off from the conductor. I want to remain as close as possible to the conductor, because then I have to take a different value of sigma. So just close to the conductor, I am seeing a charge density of sigma. Because if I am far off from the conductor, here the charge density is different from the charge density here, from the charge density here. So I would like to remain close to the conductor, or just outside the conductor. And I want to find the electric field here. Now the electric field just outside the conductor will point away from the positive charge. And I can draw a Gaussian surface. Once again I can draw a cylinder whose end cap is here. The cylinder pierces this volume. The other end cap is inside the volume. And remember, I am close to the surface. Once again, if I apply Gauss's law, the electric field at point Q, just outside the conductor, remember, just outside the conductor, if this area is A, the flux through the curved surface is 0, the flux through this surface is 0. Why is the flux through this surface 0? Aap batao. There is no electric field inside the conductor, right? There is no electric field here, so there is no flux piercing this surface. So the only flux that pierces is through this surface. Suppose its area is A. So EQA equals the charge density here, sigma times A. Which means that just outside the conductor, the electric field is sigma over epsilon naught. So just outside any conductor, the electric field is going to be sigma over epsilon naught. And it's going to point in a certain direction. What is that direction? That direction is just a normal to the surface at that point. Okay, so I can put a unit vector n and put a vector sign here. So just outside the conductor, this is the electric field. So the electric field here will be normal to the surface, here it will be normal to the surface, and this arrow, the length of this arrow will determine how much charge is on this surface. Here, if the charge density is larger, this electric field will be higher. So even though we learn about potential, even though the entire surface is at one potential, the electric field could be different in different regions near the surface of the conductor. And does the rule of electric field discontinuity also hold for this conductor? What's the electric field discontinuity here? Inside the field is 0, outside is sigma over epsilon naught. What's the discontinuity? Sigma over epsilon naught. So, and sigma is just the charge density here. So the rule that the electric field discontinuity equals 1 over epsilon naught times the charge density on a surface holds true. Now let's look at one example before we finish off this class. Suppose I have two metallic conductors. One is a sphere of radius A. The other is a shell, a spherical shell, which is a hollow sphere of inner radius B and outer radius C. And I put charge plus Q on the inner surface, on the inner sphere, and I put charge minus 3Q on the outer shell, on the shell, and plus Q on the sphere. Both of these are metallic. Now what I would like you to do, I would like you to make a graph between R, which is the distance from this center, right, where R goes from 0 to infinity, and I'm identifying a point A, identifying a point B, and identifying a point C. So I want you to find the electric field in this region, the electric field in this annular region. Annulus कहते हैं जो दरमियान की जगह. In this annular region, the electric field in the outer shell and the electric field outside the outer shell. I give you 3-4 minutes to think about this. Can you make this plot for me? ए और बी के दरमियान कांस्टेंट रहेगी इलेक्ट्रिक फील्ड. शाबाश.
क्यों होगा? शेल के आउटर में भी होगा और इधर वाले में भी होगा.
पूरे ऑब्जेक्ट को हमने -3q दिया, अब उसमें डिस्ट्रीब्यूट होना है.
मतलब सरफेस पे हम कहते हैं.
हाँ, किसी सरफेस पे होना. आप ढूंढ रहे हैं कि किस सरफेस पे होना
आउटर पे होगा या
है. किसी पे भी हो सकता है.
दोनों पे भी होगा.
दोनों पे भी हो सकता है. Just remember, I give you a hint. This sphere has one surface, whereas this shell has two surfaces, an inner surface and an outer surface. So you have to use Gauss's law and your knowledge of what is the electric field inside conductors.
There is a sphere conductor.
Yes, both of them are conductors. What's the field between 0 and A? A और B के दरमियान कांस्टेंट होगी इलेक्ट्रिक फील्ड.
सर बताया था कि अंदर क्यू पॉजिटिव है, बाहर अंदर वाले शेल में नेगेटिव क्यू.
किस तरह? 1/r² से. ठीक है, आगे क्या है? ठीक, शाबाश, गुड. आगे सी से आगे. कौन सा? अंदर वाला फील्ड है, स्फीयर.
Sir, will it be like this?
दिस इज करेक्ट. ये दोनों ठीक कर दिए आपने. ए और बी के दरमियान कांस्टेंट नहीं होगा. वेरी गुड, रियली रियली गुड. आपका नाम क्या? हाद. All right. So this is a conductor. It has charge plus Q somewhere on it. We know that the charge cannot be in the interior. So all of this charge plus Q is distributed on the outer surface. No ball point clicking, please. What's the electric field inside this conductor? 0. What's the electric field inside this conductor? 0. However, if I draw a Gaussian surface in the annular region, that is, R is greater than A and smaller than B. This is a sphere. Alright? So there will be an electric field in this region because there's vacuum here, there's air here. So now we have a sphere, a spherically symmetric charge distribution, like a ring of charge plus Q. So what is the electric field at the distance R? 1/4πε0 into Q over R squared. Q is the enclosed charge. So all of a sudden the electric field goes up and it drops by a 1/r square relationship. Remember, look at this Gaussian surface. the electric field at this point E, let's call this point P. The electric field at point P into the area of this Gaussian surface 4 pi r square must equal 1 over epsilon naught the charge enclosed. What's the charge enclosed by this dotted Gaussian surface? Plus Q. No matter where you are inside this surface, no matter where this charge is inside this Gaussian surface, the charge enclosed is Q, which means that EP is Q over 4 pi epsilon naught r squared. So there is a discontinuity in the electric field at this point. The electric field jumps from 0 to some positive number. And what is the magnitude of this discontinuity? It's going to be 1 over epsilon naught times the surface charge density. The surface charge density is Q over 4 pi a squared. So here the electric field is actually going to be equal to, can anyone tell me what the electric field here is? Q over 4 pi epsilon naught a squared. What's the electric field here? Q over 4 pi epsilon naught b squared at this radius b. And the electric field has a 1 over r squared dependence in accordance with Coulomb's law or Gauss's law. Here the electric field again drops to 0, right, because there is some surface charge on this inner surface. Now could you tell me what this surface charge should be? How much charge, how much of this minus 3q charge should distribute itself on this inner surface? Minus q. Why? Right. So out of this minus 3q, minus q charge distributes on this surface. Minus q of this charge goes on this surface, which means that minus 2q of the charge goes on the outer surface. So the charge redistributes. Why is that? Because if I draw a Gaussian surface in the interior of this conductor, what is the electric field at the position of this Gaussian surface? 0. Which means the flux through this surface should be 0. Which means that the charge enclosed by this surface must be 0. So there is plus q charge on here. There has to be a minus q charge on this inner surface, so that the charge balances out to give you an enclosed charge of 0 inside this Gaussian surface, inside the green Gaussian surface. So minus q charge goes here, and the electric field suddenly jumps between B from this value to 0, right? And the discontinuity is minus q over 4 pi epsilon naught b square, which is 1 over epsilon naught into q over the surface area of this inner sphere. So once again, the discontinuity equals 1 over epsilon naught times the charge density. Now inside, between B and C, the electric field again is 0. Now what is the electric field outside this sphere? Now this should be something that you should all be able to tell me. The total enclosed charge now is minus 2q, right? So it's a negative charge inside this Gaussian surface. So again there will be a discontinuity, and the electric field will start from a negative value. This negative value, which I would like to write here, is minus 2q over 4 pi epsilon naught c squared, and then it goes to 0 with 1 over r square relationship. So the electric field here is minus 2q over 4 pi epsilon naught r square, where r is greater than c. So this is how the electric field will vary for this problem, and this is the kind of questions you'll get in the homework and in the quiz next week. So inshallah, see you on Friday. Thanks a lot.